Hello and welcome to another lesson on my series in A-level maths, and today I'm going to be looking at an A-level further maths topic. I've picked this topic because it's one of those topics that has a lot of misconceptions, and students do find it quite tricky to pick up in the first instance. And it's a very, very important idea in maths, and it's called proof. And in particular, it's called proof by induction. So it's quite a high level idea, and it's certainly the kind of idea that students are going to be encountering a lot in A-level, when they get to university. So this is going to be occurring a lot in university level maths. Okay, so let's have a look. Now, I really love this image that they've got here of these dominoes falling over, because this really nicely illustrates the idea of proof by induction. So what proof by induction says, in a nutshell, is as follows. This is just a real simplistic overview before I get into the more complicated maths. Proof by induction says the following. If any one domino, when it falls over, makes the domino next to it fall over, okay? So that's one of the things that we need to know. If any random domino, let's say this one here, if it's picked and it falls over, will it make the one next to it fall over? Okay, that's one of the first things that we need to establish. Okay, so we need to prove actually that it will. So when one domino falls over, it will make the one next to it go over. Then the other thing that we need to establish is, can the very first domino at the start of the chain be made to fall over? And then what proof by induction says is, if any random domino falling will cause the one next to it to fall, and the very first domino can be made to fall, then what that means is that all of the dominoes will fall. Okay, that's a very, very simplistic overview of what proof by induction is. So let's get into the maths. Okay, so we have now a more formalized description of what I've just said is this as follows. It says the base case. Okay, so for proof by induction, we need the following elements. The base case. That is, basically, is the statement true for when n equals 1? Now, that's like, will the first domino fall over? Okay. The second thing is our assumption step. So we assume that it's true for n equals k. And the inductive step is, if we assume that it's true for n equals k, is it true for n equals k plus 1? Now, that's the bit that's like, if one domino falls over, will it make the one next to it fall over? Okay, and that's our assumption and our inductive step. If these things are true, if it's true for n equals 1, and if, having been assumed to be true for n equals k, it's found to be true for n equals k plus 1, then by mathematical induction, it's true for all positive integers n. Okay, that's an overview with a little bit more of a formal language. So let's have a look at an example, because I think everything becomes clearer when we have an example. So here's our first example. Prove by induction that for all positive integers n, the sum from r is equal to 1 to n of 2r minus 1 is in fact equal to n squared. Okay, so this is what we've got to do. We have got to prove this using induction. So let's look at our little menu or little guide to how we do it. We need step 1. Is what we sometimes call the base case. Okay, I'm going to write base case, which is it true? They've called it basis here in this resource. Is it true when n equals 1? Okay, because we're going from 1 to n. Okay, well, let's have a look. So what have we got? Our left-hand side, LHS, left-hand side of our equation, is 2 times r minus 1. Okay, so that is going to be 2 times 1 minus 1. So 2 times 1 minus 1 is 2 minus 1, which is 1. Okay, so the left-hand side is equal to 1. Let's see what the right-hand side is equal to. The right-hand side is equal to 1 squared, and 1 squared is equal to 1. So we found that when n is 1, that the left-hand side does equal the right-hand side. So that's good. So we can say that the formula is true for n equals 1. So it is true for n equals 1. Okay, so that's good. We've done our base case. We found out, does the formula work for n equals 1? And we found that when n equals 1, the left-hand side is 1, the right-hand side is 1. So the left-hand side equals the right-hand side. So it works for n equals 1. Okay, now let's do our step 2. Okay, step 2 is we're going to say that we assume that it is true for n equals k. So we assume that it is true for n is equal to k. So therefore, our summation formula from r equals 1 to k of 2r minus 1 is equal to k squared. And you can see that this is just the formula from above, r equals 1 to n, okay, except that n has been replaced by k. So we assume it to be true for n equals k, and therefore we assume that from r equals 1 to k is equal to 2r minus 1, which is k squared. So we're assuming that to be true. Okay, then we consider, let's now consider n is equal to k plus 1. Okay, and this is our step 3. This is our inductive step. Okay, so we're on here. You can see step 3. Show that the general statement is true for n equals k plus 1. That's where we are now. So we're on step 3, the inductive step. Okay, and we've written consider n equals k plus 1. Okay, so let's write this out. We're trying to find out the summation from r equals 1 to k plus 1 of 2r minus 1. Now, that is equal to the summation from r equals 1 to k of 2r minus 1 plus the k plus 1. Okay, so the summation from r to k plus 1 is equal to the summation from r equals 1 to k plus the k plus 1 term. And the k plus 1 term is when r is k plus 1. So it's going to be plus 2 times k plus 1 minus 1. And this is just this term here where the r has been replaced by k plus 1. Okay, so this is the summation from r equals 1 to k plus 1 is the summation from r equals 1 to k plus the individual k plus 1th term. Okay, now in our assumption step, we assumed that that was equal to k squared. So we're going to use that result now. We're going to put that result in. Okay, so this here was assumed to be, if I put that like that, this was assumed to be k squared. Okay, so we've now got k squared 2k add 1 minus 1, like that. Okay, that's our result from the other page. Okay, so now what we've got to do is we've now got to try and see if this can be arranged that instead of the n squared here in the formula, that this gets replaced by k add 1 squared. Okay, and if it can be, when we get there, I'll explain the significance of that in a second. So let's expand it and see what we've got. We've got k squared plus 2k plus 2 minus 1, which is equal to k squared plus 2k plus 1. Now, k squared plus 2k plus 1 can be factorized into k plus 1 all squared. Now, this is perfect, okay, because what we found is this is the formula that we had at the very beginning of the question that we're trying to prove, except the n squared has been replaced by k plus 1 squared. Now, what this means is that if we assumed it to be true for n equals k, we assumed it to be true for n equals k, we found that when we have n equals k plus 1, we find that the formula is in fact equal to k plus 1 squared, which is absolutely great because that's what we're after proving. Okay, so we can write, therefore, the formula, the summation formula, is true when n equals k plus 1. Okay, so that's great. So we've done our inductive step. We assumed it to be true for n equals k, and we found it to be true for n equals k plus 1. Now here comes the absolute, such an important step, okay? So this last step is crucial. It's the step on which everything hangs. And if you don't get this statement described correctly, you will lose marks for sure when you come to do it in the exam. So what we've got here, this is the sentence that's key. So we've got if the summation formula. So if the summation formula, okay, is true for n equals k, is true for n equals k, then it has been shown to be true, and I'm just rewriting the sentence here, then it has been shown to be true for n equals k plus 1. Okay, that's really important, okay, and it's very important how we phrase this. So if the summation formula is true for n equals k, then it has been shown to be true for n equals k plus 1. Now the next bit's crucial. So this is as the result is true for n equals 1, okay, because you remember we found the left-hand side equals the right-hand side. As the result is true for n equals 1, okay, it is now also true for all n is a member of Z plus by mathematical induction. Okay. Now, what is Z plus? If you remember Z plus, I think there's a little description here. Z plus is the set of positive integers. Okay, so i.e. It's the numbers 1, 2, 3, and so on. Okay, so it's equivalent to the natural numbers, a set of natural numbers. So Z plus is the set of positive integers, which is equivalent to n, the natural numbers, or sometimes called counting numbers. Okay, so perfect. So yeah, so going back to our domino analogy from the start of the lesson, this is basically saying if we pick any random domino, it has been shown that the domino next to it will fall over. As the first domino will fall, therefore all of the dominoes will fall over. Okay, that's just like what that means in layman's terms. Okay, so if the summation formula is true for n equals k, it's been shown to be true for n equals k plus 1. As the result is true for n equals 1, it is now also true for all n is a member of Z plus by mathematical induction. Absolutely crucial that you get the wording of that statement correct in order to get the marks, because the examiners are very pernickety about how you express that. Perfect. Right, let's have a look at a second example then. We're going to be following the same process, okay? So we're going to use mathematical induction. So let's look at another example. Here we go. Example 2. Prove by induction that for all positive integers, the summation from r equals 1 to n of r squared is equal to 1/6 times by n times n plus 1 times by 2n plus 1. Okay, so this question is to prove that the summation from r is equal to 1 to n of r squared is equal to 1/6 n times by n plus 1 times by 2n plus 1. Okay, so step 1 is our base case. Okay, so I'm going to write down the base case. In other words, is it true when n equals 1? Okay, so what's our left-hand side going to be? Our left-hand side is just going to be 1 squared, which equals 1. Okay, so that's fine. It is true for the left-hand side is 1. Let's see what the right-hand side equals. When n is 1, we're going to have 1/6 times by 1 times by 1 add 1 times by 2 times 1 add 1, which is equal to 1/6 times 1 times 2 times 3, which is equal to 6/6, which is equal to 1. So therefore, we found that the left-hand side equals the right-hand side when n equals 1. So therefore, the equation, the summation equation, is true for n equals 1. So we've proved now the base case. Okay. Now it's step 2, our assumption step. Step 2. We're going to now assume that it is true for n is equal to k. So we're just going to pick some value k, we're just going to assume it's true. So that means that our formula now becomes the summation from r equals 1 to k of r squared is equal to 1/6 k times by k add 1 times by 2k add 1. So all that's happened here is it's the formula from above, but the n has been replaced by k. Okay, so that's our assumption step. Now it's time for our step 3, our inductive step. So we're now going to say consider n equals k plus 1. So now we're going to consider n equals k plus 1, which is our inductive step. So we're going to have the following formula. In fact, I'm going to start on the top of another piece of paper because this is going to get a bit longer here. Okay, so we're there we are, consider n equals k plus 1. So our formula is now summation from r equals 1 to k plus 1 of r squared is equal to the summation from r equals 1 to k of r squared plus the k plus 1th term, okay, which is the next term. So therefore we have k plus 1 squared. Now that's our next term, that's our k plus 1th term, okay? Good, so now you may remember from our assumption step here, we assumed it true for n equals k. We assumed that this bit is equal to this bit. So we're now going to put that result in there exactly like we did last time in the previous example as well. So we're going to assume we have 1/6 k times by k plus 1 times by 2k plus 1 plus k plus 1 all squared. So we've just made use of our assumption step there, okay? Now, at this stage, there's two ways we could approach this at this stage. At this stage, we could literally expand everything and try and factorize it and hope that we get this expression here, but everything replaced by k plus 1, okay? But I would recommend a much better approach is to factorize, to try and look for the biggest factor that you can take out. And I hope you can see that we could take out a factor of k add 1 from this first term and k add 1 from that second term. So let's do that first. So k add 1 times by 1/6 k times by 2k add 1 plus k add 1. Okay, so I've factorized out a factor of k add 1. Now, I'm going to use a sneaky little trick here, okay? What we could do is it'd be nice, because we can see our formula starts over here with 1/6, it would be nice to take out a factor of 1/6 as well. But we've got a 6 here, but we haven't got a 6 here. So what we do is we use a kind of like sneaky little trick. We engineer a 6. And the way that we engineer a 6 is by writing 6/6. Because remember, 6/6 is 1. So because 6/6 is just 1, we can just invent a 6/6, which means we can now take out a factor of 1/6. So we have 1/6 times by k add 1 times by k times by 2k add 1 plus 6 now times k add 1. Okay, now at this stage, we do have to expand everything now. So we've taken out a factor of 1/6 k add 1. Let's now expand this and see what this is going to simplify into. So let's expand it and see what it turns into. So we have 1/6 k add 1 times by 2k squared add k, 2k squared add k, add 6k add 6, which goes to 2k squared add 7k add 6. So 2k squared add 7k add 6, okay? Which in turn, we can either use our calculators to help us factorize that, or we can use inspection, or we could use an algebraic method. But this, however we do it, it factorizes into k add 2 and 2k add 3. Okay, and we've got 1/6 and k add 1 there from before. Okay, perfect. So what we've done now is we've kind of like got as far as we can go with that. And what we've got to try and do now is look back at our original expression here. Okay, 1/6n times by n plus 1 times by 2n plus 1. And we really need to try and say, can this whole equation be that everywhere where there's an n, it gets replaced by k plus 1? Okay, so we want where there was an n, we want to replace it by k add 1, okay, in this equation. Well, we've got 1/6, and we've got where there was, I'll write down the original formula, what it was like before. Okay, so that's the original formula. So we've got here k add 1, so that's fine. So we've replaced the n with the k add 1. I'm just putting this here for comparison, okay? That's just so we can see for comparison. That's fine. Now, k add 2 can be thought of as k add 1 add 1. Okay, so k add 2 is k add 1 add 1. So that is the n has been replaced by k add 1. So that's good, and that's looking really good. Okay, now here, 2k add 3, this 2k add 3 can be thought of as 2k add 2 add 1. So 2k add 3 equals 2k add 2 add 1, which is equal to 2 times k add 1 add 1. And that's perfect. That's really, really good, because we've got 2 times n is now 2 times k add 1. So we put that with 2, open brackets, k add 1 add 1. And that completes it, because everywhere that we had an n in the original formula has now been replaced by a k add 1. Okay, so that's perfect. So what that means is, that means that therefore the summation formula, so the summation formula is true for n equals k plus 1, because we assumed it to be true for n equals k, and we've just found that it is true for n equals k plus 1, okay, which is perfect. So now it's time for the conclusion statement, okay? Very important, remember, that we get the wording of our conclusion statement correct. So I'll just bring it over here. So we can now write our conclusion statement, okay? And this is it here that I'm reading out from here. This is the really important bit. So it says, if the summation formula is true for n equals k, then it has been shown to be true for n equals k plus 1. As the result is true for n equals 1, it is therefore true for all n is a member of Z plus by mathematical induction. Okay, so we've proved that if we assumed it was true for n equals k, we found it was true for n equals k plus 1. As the result was true for n equals 1, it is therefore true for all n is a member of Z plus by mathematical induction. Okay, perfect. Okay, that's really good. Now, I would just point out that we've looked there at one type of proof by induction, but just to make you aware that you might well be having to look at other types of proof by induction. So, for example, we could use a different type of proof by induction, still the same ideas, but proof by induction can also be used for divisibility problems. Okay, So that's another type of proof by induction. And then the third type is matrix with matrix algebra. Okay, so yes, proof by induction can be used in matrix algebra as well. Okay, so that's another example of the third kind of example of where we can use proof by induction. Perfect. Okay, well, I hope that you found that lesson useful. I will put a resource in as well that has lots and lots of practice questions for you to accompany this lesson. But yeah, thank you very much for listening to this introduction to the very important topic of proof by induction. Thank you.